Today I'm going to discuss torque acting on electric dipole placed in uniform electric field. Say this is a uniform electric field from left to right. An electric dipole is placed like this. It's not always torque will act on it. See, if the dipole is oriented like this, so what will happen is the force acting on Q charge will be this way, it's a QE. And force acting on this minus Q charge will be the same QE but in opposite direction. In this situation, what is the force? What is the net force acting on it? What is the net force acting on it? It's a zero. And what is the torque acting on it? It's a zero. No torque. So it's not always if any dipole is placed is going to experience a torque. When it will experience a torque, see, this is a uniform electric field. This is a uniform electric field and a dipole is placed like this. Say this is minus Q charge, it's a plus Q charge, and separation is, say for example, 2A. This is a uniform electric field and this dipole you can see now it makes angle dipole moment, electric dipole moment makes angle theta with the uniform electric field. See, what will happen is this Q charge will experience force QE in this direction and the force QE in opposite direction. Now this dipole will experience torque. If I ask what is the net force acting on this dipole, again the net force will be what is coming out to be zero. Okay, it will just experience a torque. Okay, and what will be the torque? Now we are going to study what is going to be the torque. The torque, the net external torque would be how we define the force into perpendicular distance. Let's say I'm asking the net torque about the point O. Net torque about the point O. So we'll say the force into the perpendicular distance from point O, and so you can see what is the perpendicular distance from the point O is going to be the force, and what is the magnitude of force? This magnitude of force is it's a QE into the perpendicular distance is going to be it's a 2A sine theta. Q into 2A, we know this is electric dipole moment. So we can write this is electric dipole moment into E sine theta. You can also write then in the vector form what will be the net external torque is going to be. It's a PE cross E. PE cross E. And what will be the tendency of this torque? Tendency of this torque is to align the dipole in the direction of external electric field. Now we're going to discuss what would be the potential energy of a dipole placed in uniform electric field. Potential energy of a dipole placed in uniform electric field. We define it like this: potential energy of the dipole in uniform electric field. We define it like this: potential energy of the dipole is amount of work done in rotating the dipole from amount of work done in rotating the dipole from a standard position. What is this standard position going to be? Is taken is taken perpendicular to the direction of electric field. So again we remind, potential energy is the amount of work done in rotating the dipole from a standard position to a final position. So how we define the potential energy to be? The potential energy we represent by the U. This is nothing but equals to the amount of work done in rotating, amount of work done by the external force. This is by the external force. Because if we work done by the internal force, if we use, then we have to write here negative sign. So potential energy equals to work done by the external force, and we know how we write the work done. It's a tau d theta. From standard position where I have taken, it's a from pi by 2 to some other position, let's take phi. So the potential energy is going to be as a torque. It's a Pe sine theta into d theta from pi by 2 to some phi. Let's take it out constant terms bar outside. Integration of sine theta, it would be minus cos theta from pi by 2 to some phi, which is equals to minus of Pe, it's a cos phi minus of Pe. I have written it's the electric dipole moment Pe into electric field also, cos phi minus 0. Okay, so what is the potential energy to be equals to? It's a minus of electric dipole moment into the electric field into cos phi. In the vector form you can write it's a minus of Pe dot E. It's a minus of Pe dot E. You can say if it, what would be the maximum potential energy? It would be for theta phi to be equals to pi, and that would be Pe into E. At position phi equals to pi by 2, the potential energy is going to be 0, and at position phi equals to 0, the potential energy of the dipole would be minus Pe into E. You can see in all these three situations, at this situation when phi is 0, this means what? Electric field and the dipoles are in the same direction. Then in this situation you can see the potential energy is coming out to be minimum. That means the dipole can stay in stable equilibrium. Here the potential energy is maximum, so this will be unstable equilibrium. And that's the way how we write the potential energy of the dipole. This is an important topic for the 12th CBSE board. Okay, so don't forget to subscribe and like my video. In next session we'll discuss the electric potential.